Hey there, students. Okay, so we are continuing in 10.3 with the idea that the first part, or the first even couple pages of 10.3, which is again calculus, I'm in trouble writing here, in polar coordinates. The first couple of pages was about finding the slope of a tangent line to a polar graph. And so what we're going to do now is focus on integration and how that applies. In particular, it's going to apply the way it first applied for us with regular functions in sort of finding the area under a curve. So let's sort of imagine the goal and then how we're going to try to get it done. So let's say we had, I'm going to sort of map an arc like this. Doesn't have to be circular, but just imagine you're looking at some particular piece of a polar graph. And that we're going to imagine sort of from one particular angle, which we'll call alpha, and then up through another particular angle, which we'll call beta. Like A and B, but alpha and beta when we're talking about angles. And that we're going to have a goal of trying to figure out how much area is in here. So this is our region. So unlike when you're using X and Y, where everything is sort of horizontal and vertical and you have a nice area under a curve, here, as the curve is drawn, you're changing in an angle, so this means that the region that you're sort of getting an area of looks something like that. Okay, so the question is, how would we get the area swept out by a particular part of a polar function as you went from angle A to angle B? So let's relate this to the original area problem that led us to integration. So in an original area problem, you had an A and a B, and you had a function, f of x, and you wanted the area under the curve here. And so to get the area under the curve, we subdivided our input variable into intervals, and then in each interval, we chose a particular height of the function to represent the height of a rectangle in that subinterval. Maybe it was the lower value, maybe it was the upper value. And then we'd use the area of that rectangle as an approximation for the area under the curve. And then we would add those up with a summation. And then this was all where delta x was the sort of thickness of these slices, leading to the thickness of these rectangles. And then as delta x went to 0, we took the limit. As delta x went to 0, and these got skinnier and skinnier, of the summation of the rectangle areas, which was the height of the rectangle, at some delta x star, times the thickness of the rectangle. So this produced a Riemann sum, and we took the limit as this happened, and that gave us our integral. So that was the basic idea. So the thing is, we don't really, by changing the x values, we had up and down lines that created rectangles approximating areas. So if I subdivide the change in the variable of an angle from alpha to beta, then that looks like this. And so then if within each of those little subdivisions I choose a particular r value and fix it for the subdivision, maybe it's the upper value, like in this first subdivision, if I choose that r value, then if I hold that fixed for that first change in the variable, I get this. And then maybe in here I would choose this r value, and then in here I would choose this r value, and then in here I would choose this r value. So then as I fix little r values in each of these subdivisions in the angle, I don't get a rectangle underneath them. I get what looks like a sector of a circle. So rectangles were nice and easy because they were just base times height. But here, I'm subdividing a change in theta into little delta thetas. And based on the thickness of the delta theta and the fixed r value for some choice in there for some theta star instead of x star, then I have to get an area of a sector. So then I would basically say I want to get the area under r in this sector, and then I want to add those up as an approximation for the area under the curve. So that gives us a need to know the area of the sector of a circle. So if I have a circle and I have some sector of the circle, meaning you have some delta theta in here, some amount of angle, well, the area can be seen with a little formula. So basically, you have the area of the whole circle is, well, again, I guess we have to use the fact that there's an r. So it's pi r squared, right, is the area for the whole circle. But that could be thought of as, you can actually just think of it as a portion where the r value is this length here, right? So the area of the whole circle is, let's do it this way. Whole area is pi r squared. But we don't want the whole circle. We just want the portion that's in the circle. And so that depends on how big delta theta is out of the 2 pi area. So for example, if delta theta is 1/3 of the whole way around, then delta theta would be 1/3 of 2 pi. It just depends on what the angle theta is. So whatever this delta theta angle is here, if you take delta theta and divide it by 2 pi, then that's the portion of the circle in the sector. Again, I should have pointed that out here. So this is called a sector of a circle. Maybe some of this is familiar if you ever did some geometry stuff, but probably not. I'm assuming not. So, for example, if I have pi over 2, that would be right there. Pi over 2 divided by 2 pi is 1/4, which, because pi over 2 from here to pi over 2 is 1/4 of the whole circle. So this fraction is however much angle is in the sector divided by the entire angle of the whole circle is 2 pi, creates the portion of the circle that's in the sector. And so I multiply that fractional amount times the whole area to get the area of the sector. So area of a sector is the portion delta theta over 2 pi times pi r squared, which is the area of the whole circle. So if we simplify this a little bit, because these pi's go away, so that's nice. It doesn't simplify much more than that. Then we just get 1/2 r squared delta theta. So this is the formula for the area of a sector. And so this would be what we would use to approximate the area of a particular sector with a fixed r value. We'd use that r value in this formula for the area of a sector. The same way we used the idea of the height times the base to get the area of the little rectangles under the curve. So this would lead us to, see if we can follow along here. Again, I should give you some reference. This is all on, they start this discussion on page 734, a couple pages into the section. So let's go page 734, since I didn't say that before. Point that out. So that means in each one of these little delta theta sectors of the area that I'm trying to get, I would have 1/2 And then the r value that I use in a particular one of these subintervals, the r value I use, I get by plugging some theta star from in that angle range into the function. So let's remind ourselves of our notation for this. You have r is equal to some function of theta. And so we would plug a particular theta star into that function of theta. So I'm going to put f of theta star. And that's squared, because r squared, it's 1/2 r squared times delta theta. So this would be the area in the subdivision, one of the subdivisions where you took a theta star from that subdivision angle. And then you would get this area of that piece. So then I want to add these up. Basically, as n goes from 1 to infinity, I'm going to add these up. And then I'm going to take the limit as n goes to infinity, or the limit as delta x goes to 0. Those are equivalent. In this case, it's not delta x anymore, it's delta theta. So then I take the limit as delta theta goes to 0 of this number of subdivisions, and that'll give me the area swept out under the curve. So just like it did in Chapter 5, this leads to an integral. So this becomes the integral from alpha to beta of 1/2. And I'll use the f notation, or you can think of it as r of theta, or f of theta is equal to r. So this would be f of theta squared d theta. So for most of you, it'll be kind of hard to feel real comfortable, certainly at any quick time at all, as to why this works out the way it does. But this is a formula, so let's they actually give it as a formula on page 735. And this is for the area under a curve down to the origin. Now, actually, in the formula, even before setting this up, they immediately advanced this so that we could imagine, well, what if there was another curve here, and we wanted the area between these two curves? And like we did in Chapter 6, when we did the area between two curves in a Cartesian system, you would just take the outer curve area and then subtract the inner curve area away. So the formula they give on page 735 actually is the integral from a to b, or a to alpha to beta of 1/2. And they go ahead and take the difference of the functions. So you'd have f of theta squared minus g of theta squared d theta. So that would be where you had the difference between two functions. So that's if your inner function here is g of theta, and then your outer function over here is f of theta. And so this gives us a formula for the area swept out under a polar curve, as it's, if you imagine being swept out between the curve and the origin, or between an outer function and an inner function, either way. So that's a lot to think about, but initially it just gives us a formula, and if you don't have two functions, if you only have one, the formula is pretty simple. It's not too complicated. You just square the function, multiply by 1/2, and take the integral. And so I think it'll get more comfortable because the formula is not cumbersome to use as we do some problems. And so, and this whole rest of the section is like a little less than 4 pages. The whole section is about 6 pages long. And so the first 2 pages are for the slope of the tangent, and the second 3.5 to 4 pages are for what we're discussing right now. And in that time, they do several examples for you. But again, I'm going to grab something from the exercise set to do as an example. And I'm imagining we will need more space. Maybe this is good enough. I think, yeah, oftentimes we want to draw a graph. So let me clear this page, and then I'll rewrite our formula that we came up with so that we can still use it. So what we just came up with, at least for a single function, and we could also use it for the difference between two functions if we need to, is that the area under or swept out of or by under a polar graph, just having trouble writing, of r equals f of theta from alpha to beta is, I'm going to pull the 1/2 out front, the integral alpha to beta of f of theta squared d theta. So fairly simple, and then of course we can use the difference if we need to. All right, so let's see. I'm looking at page 738 here, and this is the exercise set. And again, we're finishing up 10.3 here for some reference. So in the beginning, the beginning problems are the slope of the tangent, because that was the beginning part of the section. So the areas of regions, 21 through 36. Let's look at 27. So it says, make a sketch of the region and its bounding curves. Find the area of the region. Okay, make a sketch of the bounding curve and find the area. So in 27 it says we're supposed to find the area of the region inside one leaf of r equals cosine 3 theta. So we want area inside one leaf of r equals just cosine 3 theta. Cosine 3 theta. So first we want to make a sketch. So let's make a sketch of this, and I assume it's going to produce some leaves. And then we want to get the area in one of these leaves. All right, so again, now we kind of get a little review of what we did in the previous section. So I'm going to imagine for myself that I put in some thetas and I get some r values, but that I'm also going to sort of imagine the overall range of this function, and then I'm going to try to make a sketch. So for example, if I make a littler sketch of the r value versus the theta value for cosine 3 theta. So if I go all the way around the polar graph once, that's going up to 2 pi, and hopefully we'll see if that completes the graph when I've done that. However, the cosine of 3 theta, cosine has a 2 pi period value, but if you put in 3 theta, then the period is 2 pi divided by 3. So let's see. So if I take this range of 2 pi and I divide it by 3 like this, then each one of these segments is going to be a complete cosine cycle. So 2 pi divided by 3, divided into thirds. So that's 2 pi. This one would be 2 pi over 3. Then 4 pi over 3, and then 6 pi over 3, which is 2 pi. And so that's now my new period when I have a 3 inside the cosine. And cosine isn't multiplied by anything, so we're going to go up from a 1 and down to a -1, and it's going to do its normal full cycle every 2 pi over 3. So it's going to go from here down to there and then back up to there, and it's just going to keep doing that 3 times. Okay, so A little sketchy here, but I'm going to chop this up a little bit better. So that means that it starts at a 1 and goes down to a -1 when it's halfway between 0 and 2 pi over 3. So that means the middle is pi over 3. And it's going to hit a 0 at pi over 6. A little sketchy. I'm just doing this on the fly. Okay, so here's our graph. So I have a max R value of 1. So instead of 1 being this little teeny circle, let's say my 1 value is 2, 3, 4, 5, 6, 7, 8. Let's say here. So I'm going to say I go out to here. And that means that's up here is a 1. And here is a 1. And 8 down. 1, 2, 3, 4, 5, 6, 7, 8. And here is a 1. So there is my radius of one circle. And so when I plug in a 0 for theta, then I get cosine of 3 times 0. Cosine of 0 is 1. So I start here. And then as theta goes from 0 to pi over 6, I can see in my graph here, 3 times pi over 6 is pi over 2, and cosine of pi over 2 is 0. And so that's why when I get here, I'm at a 0. So that means when I go up to pi over 6, so here I have 0. This angle is pi over 12. This angle is pi over 6. And so that means by the time I've moved from here, from 0 up to pi over 6, the radial length has dropped from 1 down to 0, so it's going to do something like this. So that'll happen as I went from 0 to pi over 6 in angle, then it went from 1 down to 0. So that, and then here I got a 0. So then when I go from pi over 6 to pi over 3, then the value drops from 0 down to -1. So it's negative that whole time. So during that time, R is negative, and I'm backing up. So that means as I go from pi over 6 here up to pi over 3 here, as theta goes in that range, the function is backing from the first quadrant down into the third quadrant. And as it goes from here to here, in that range, it's going down to a -1, peaking a -1 when I get to pi over 3. So at the pi over 3, I would go backward on that line down to a 1, which would be to here. And I'm going to be backing up as I switch in there like that. Something like that. So now I've just sketched out the graph in the pi over 6 to pi over 3 range. And then as it goes from pi over 3 back, it'll go back to 0 and back up to a +1 as it goes all the way to 2 pi over 3, just to sort of go through that whole cycle again. It'll end up back at a +1. So it'll do both of the arcs that I just showed here as it goes over to 2 pi over 3. So we have pi over 2. 2 pi over 3 is here. So this angle here is where I'm at 2 pi over 3. And as the angle theta sweeps from here to here, then I'm going to go back to 0 and then back out to a +1. So let me make some space. So here, that means this. I'm going to have a point at +1 there, which is right there. And that this is going to be sweeping back at first. And then after it goes back, it will sweep out to there. Okay, interesting. All right, so then that's basically one full cycle, one full period of the cosine 3 pi, and the angle range that I did here was this. This was the entire angle range from 0 to 2 pi over 3, and during that time it started at the 1 on the right here, went in through the origin, went to the -1, into the third territory when it was negative, and then went back up to 1 as it got to there. So then as it goes from 2 pi over 3 over to 4 pi over 3, it's going to do the same thing again. It's going to go through that exact same cycle of values. Instead of starting at the 1 on the right, I'm now starting at the 1 in the second quadrant. So let's clean this up a little bit. Take away this angle discussion stuff. So now I'm going between 2 pi over 3 as an angle. 3 pi over 3 is at pi. That's pi is 3 pi over 3. And then to 4 pi over 3, which is the one over here where we were opposite 1 pi over 3. So here we're at 4 pi over 3. So as I go from here to here through those angles, as theta passes along this angle arc rotation, then the graph here is going to go into the origin, out to a 1, and then back through again. So as it starts in this journey, from here I'm going to go back down to the origin like that. And as I continue on that journey, I'm going to go back out until I get back out to the 1 here. And then I'm going to go back in, but I'm starting to retrace over the graph I already had now. And then I'm going to go back out to there. And that's where I will get when I finish at 4 pi over 3. And then the last range, it'll just repeat over the same graph. When I go from 4 pi over 3 to 2 pi, or back to 0, then it'll go from 1 back to the origin, back up to quadrant 2, back to the origin, and back out to the first point that we started with at the beginning. So basically, it starts retracing itself even before it finishes, and it's just redrawing over the same thing. So this is a sketch of this graph. And we are tasked to get the area of one leaf of this graph. Take all this stuff out of the way. So we want the area inside one leaf of this function. So what we need to do is figure out what range of angular values I would use to come up with this. So for example, this arc here that we started with, we did this part when we went from 0 to pi over 6. That gave us this part right here. And so if I did the area under that part of the curve, between that part and the origin, as we did that range, I would get this area here. Because I would be looking at these arcs as the curve went through this range, and it would give me this area as it swept from the 1 to the 0. So actually that's all we need, because based on symmetry, that's exactly half of what we want. That's half of one of these leaves, even though I shaded a little bit more than half there. I got a little exuberant. Let's see if I can... Oh, that wasn't too bad. But yeah, so if I think about this line, then we can see that the part that would be shaded when we do that part of the graph is half of one of the leaves I want. So by symmetry, I could just do that part of the function over this range and just double it to get one whole leaf, to get the top and the bottom of this leaf. So I'm going to say then, doing that process, that the area that I want, the area inside one leaf of the function, will be 2 times the part I get from 0 to pi over 6. And using this formula, I would do then 2 times, I would do 2 times 1/2 the integral, and alpha to beta is 0 to pi over 6. And then the function is cosine 3 theta, but that's squared in our formula d theta. So let's pause there for a second. Let me put my closing parentheses. So this is how I used the formula for the area under a polar function to set up an integral that would determine the area in one leaf of this particular function. I had to know what limits of integration I had to use. I could actually instead go from 0 to pi over 3, and then that would give me the whole thing, because that would, if I went from 0 to pi over 3, then that would give me that arc plus this arc. And if I did those two arcs, I would get a leaf. So you could even test that after we do this to see if going from 0 to pi over 3 would give us exactly twice the answer we get if we only go from 0 to pi over 6. I believe it will. But we can also just do it the way I said and then double our answer. So we're still going to need to evaluate this integral, but now it becomes, a Chapter 7 problem. Now it's just an integral to do. So you can pause the video here and think about it. Normally, if I was in class, I'd see if there were any questions at this point, but I'm just going to march on, and then hopefully you'll have a bunch of questions for me on Wednesday if I need to explain anything better. So continuing on. So to now work on this integral, just so that we go ahead and finish this problem. Well, nicely, I have a 1/2 and a 2 that kind of cancel out. And if I were to do this integral, I see that I have a 3 theta in here instead of just a theta. So I would want to do a u substitution to get that constant out of there. So I'm going to let u equal 3 theta. Then du is equal to 3 d theta, or d theta is equal to 1/3 du. So then if I make that swap, then I get the integral, and I have cosine of u squared, and then I have du over 3, but I'm going to put the 1/3 out front. Now, I could integrate this and then back substitute, or as I like to usually suggest instead, which is what I will do, I could change the limits of integration. So before, with my limits of integration, we had theta equal to 0 and theta equal to pi over 6. So when theta is equal to 0, 3 times 0 is 0, that means u will be equal to 0. So I still start with 0. And when theta is equal to pi over 6, and I plug that in for theta, I get 3 times pi over 6. 3 pi over 6 is pi over 2, so that means the upper limit for u is pi over 2. So now I changed the integral of cosine 3 theta squared d theta from 0 to pi over 6 into the cosine u squared du from 0 to pi over 2 with the 1/3 out front. Okay, so cosine squared u, or cosine u squared, that's like one of our trig integrals back from, 7.3 or something. So we could do that, but I think I can almost remember the result. Actually, let's use our table of integrals so that we don't have to redo work that we did before. Which one is that? I'm just flipping in the book so we can look it up. Trigonometric integrals. So that's number 30. So on the table. So number 30 on table of integrals. And that would have us evaluate this by doing, let's read this here. So cosine squared x dx, except this case we have a u, is x over 2. So I'm going to write u over 2 plus sine of 2x. So I'll write sine of 2u divided by 4 plus c, but we're going to let c be 0. And we're going to take this and multiply it by the 1/3 out front so I don't forget it, and we're going to evaluate from 0 to pi over 2. Okay, so this gives us our way to get the area under one leaf on this 3-leaf clover that we had for our function. So this is going to be 1/3 times pi over 2 divided by 2 plus sine of pi over 2, and that's times 2, I switched the order in there, all divided by 4, minus 0 over 2 minus sine of 0 over 4, plugging in the 0. And pi over 2 times 2 is pi, and sine of pi is also 0. So actually, this term is a 0. These terms are clearly 0. So all I get is, so 1/3, and pi over 2 divided by 2 becomes pi over 4. And then if I multiply those, I get pi over 12. That's our answer. So what was that we found? Again, that was the area inside one leaf of r equals cosine 3 theta. And after we drew a sketch, we kind of saw that that makes sense because this does make a 3-leaf flower, or whatever you want to think of it, 3-leaf clover, I should say. And so we got one of the leaves by taking the first half of a leaf that's drawn by the function and doubling that amount of area to get one whole leaf. This was exercise number 27 from the exercise set. And hopefully we'll do more examples based on your questions on Wednesday. But here's where we'll stop. So what did we do? The last 4 or so pages of 10.3 involve getting the area under a polar graph. And we looked at that idea and came up with this formula, and then did this example to put it into action. So hopefully study this, do some more examples, and come with questions on Wednesday. And at this point, we will end the video.